Hello, welcome to our first problem in Ampere's law. So first we're going to learn how to calculate circulation of a magnetic field. So this is an exercise in given. So exercise is a given magnetic field, given an expression of magnetic field is a vector, right? Vector field, magnetic field. Calculate a property called circulation, and it's about around a closed loop in space. So that's what circulation is. Circulation. So this thing is really not stated, but just a calculated circulation. Okay, so circulation. So there are three problems here we want to do. So we've given this magnetic field with some kind of description here. Yeah, that goes with this coordinate system. So this is the coordinate system. It's arbitrary point P, and S and phi are described this way, and of course this part is Z. Do around this one. So this is A. The problem A is this loop. Problem B is a little more complicated loop. You go around and then go this way and then keep going and come back this way. So it's like a semicircular but connected by these lines. Okay, and then this one is even more interesting. Is say you start from here, you go this way, and then you go up in that, and then you go in this other one and then come back here, and so this is a closed loop. So there are three problems here, and I want to compute all three of them. So if you know the answer, how to do it, go ahead and do it, and then come back and kind of look at my solution. Okay, so I'm going to kind of clean this place up and do the problem. Okay. All right. Just a reminder that if you haven't subscribed to this channel, please help grow this channel by subscribing. If you like my explanations, definitely you should hit like button. And you want to know more, you study more physics like from this perspective, you can go to this website where I run this website. Okay, so what we have here, let's look at this situation. What's the definition of circulation? So circulation is a mathematical property, and circulation stands for this integral, and it's a closed integral, so sometimes put a circle like this, and sometimes people like to put, because it's got orientation, it's not just a circle or closed loop, it's got orientation in space. Okay, and so you've got any field dot dl. So it's kind of a line integral. What is a dl? Dl is, so this loop, then you pick a small element. So this is a formal definition, right? You can't really do an integral here. This is a formal. You got to set it up. So this is dl. You remember this was, in the case of Biot-Savart law, this was actual circuit in the current going. But here this is in space. There's no physical thing there. There's just a loop in space. Okay. So dl is this vector on this path. If this thing is going in the direction of this path is this way. So this oriented path. If I go in the other direction, I will get a negative answer actually to what this path will give me. So this is dl. dl is this vector here. If I'm over here, the dl is that vector over here. So there it's changing as we go around, okay? And so if I were here, so this vector, let's say it's a magnetic field, okay? So this vector will be over here that way. Maybe over here this is that way. Maybe just pick another direction for the over here is that way. So on here you'll get a 1 b dot dl. Over here you can get another b dot dl. So you can imagine breaking this thing up into small pieces, and so this is basically sum over b dot delta l's over this whole path. You can call it circuit C over circuit C. All right, so let's work out this this example. So what we have here is we got x and y, and so this is the path we have to go over, and so I'm going to pick a dl at some angle phi, and so this distance is SA. So dl will be some angle d theta, d phi. I'm going to use angle phi for that. And so dl, this dl here, magnitude will be SA, SA times d phi, right? This is on the arc, and angle is d phi, and the radius is SA. So that's dl. And what's the direction? So direction is this direction, and this angle is phi. So if you translate that direction all the way down here, so if this is phi, then this is phi, and this is the y-axis, and this is the x-axis. So unit vector in that direction will be we will call it sometimes we just call it phi hat in this notation, but unit vector will be in terms of x and y will be minus sine phi j hat plus cosine phi, and this is I hat j hat is going to be like that. It's going to be this. So this actually is mu naught I over 2 pi s unit vector, and we're just going to call that unit vector along the phi direction. So the dl vector is at that point it's just SA d phi unit vector in the phi direction. So this is the magnitude, and this is the direction. So unit vector. Now, by the way, idea of writing a vector as a magnitude and a unit vector is very important. You should definitely master this, because then your analytical skills will really get a boost, because then you use unit vector as a multiplier to the magnitude, and then you can do algebra with it. Just very nice, okay? It takes a little getting used to it, but it's worth it. So as you will see now, so I'm going to do this integral. So the b is given like that. So b is b dot dl is simply mu naught I over 2 pi. S is SA at this point. I'm looking at what the b is. S is SA, and I got u hat phi, same direction as that, dot SA times d phi u hat phi. So now the dot product is between these vectors, and that's equal to 1. So this just becomes mu naught I over, and SA also cancels out this SA. So you got 2 pi d phi, just like that. And this. Now, when I go in here, I go from phi equal to 0, all the way to phi equals to 2 pi. So I'm going 0 to 2 pi. So when I do this integration over this turns out integration over this variable, right? And that's going to be 0 to 2 pi because of now this is abstract, formal, and this side becomes specific, no longer formal. Okay, so now doing this integral is really really simple because this is constant, doesn't depend on phi. So this is just mu naught I over 2 pi times 2 pi and just mu naught I. So answer to A is circulation of B field around CA is equals to mu naught I. Okay, maybe you want to try to do B on your own. Now you know how things will go. So B, you can see there's going to be one part, and then you're going to be part here, then you're going to be part here, and then you're going to be part 4. So circulation of B dot dl turns out to be integral over 1 plus integral over 2 plus integral over 3 plus integral over 4. So over A is going to be almost like this, but only going to 0 to pi. So I don't need to repeat the work. So this will simply be mu naught I over 2 pi times pi, and 3 will be mu naught I over 2 pi times pi. Then we need to figure out what to do about this guys and this guys, right? So let's look at this guy. So on that, so we're going from here to there. So take a small piece. The dl is some distance, say is some distance s. This was SA and this SB. So S goes from, so but this one is at S, and so dl is going to be S. I'm going from SR dx I hat, and B is whatever that whole thing is B u hat phi. So B is this way, B vector is this way, dl vector is that way. B dot dl at any of these guys is actually 0. So integrate that 0, so it's going to be 0, and this is going to be exactly same thing over here. There's also going to be 0, and so when I add these up, I get again mu naught I. So this is a different circuit than that, but we got exactly same answer here. So this is circulation of the B field using this path. CB is also mu naught I. Okay. Now, how about doing this guy? Maybe you want to do this now. Okay, so to do this now, you can see that I can do again the same way. Do the 1, then I go to 2, then I go to 3, then I go to 4. So this will again be equal to 1 plus 2 plus 3 plus 4. So this we are doing b dot dl over this this loop. Okay, so one I go from, it's going to be almost like that, but we're just going up to here, and we are going counterclockwise, right? So if I go in counterclockwise, I'm going with 0 to pi over 2. So the 1 should be equal to mu naught I over 2 pi times pi over 2. This part should give me 0 as before. Now this part is the problem here, right? Here we're going, it looks like it's going to have the same answer as that, but no, it's going opposite direction. So this is actually minus mu naught I over 2 pi times pi over 2. And you need to know why I got a minus sign. And then this will be 0. So this, when I add the whole thing up, I get a 0 here. So this one is circulation is 0. Okay, so how did I get a minus sign here? This one plus is okay because last thing. So let's do that out. So let's do that out. I have, so this is the on the 3. So I'm going to go this way. And this again S, and this is d phi. This is dl. So you can say dl if I want to do it like this, and but the b is in that direction. So dl is going to be opposite to b. B is some b u hat phi. So dl will be minus s d phi u hat phi. So when to dot product b dot dl, I got minus s is s times s of b minus s of b times b d phi. So phi goes from, phi is 0 to pi over 2. That's the range. Often you're going to have a problem here. Either you include the phi in the increasing, or you include the direction in the dl. You can't have the, if you do phi goes from pi over 2 to 0, then you're going to double count the direction. So this will actually give you the wrong answer. So let's work this out. So minus s mu naught I over 2 pi sb times sb, and then you have a d phi, and then I need to have the direction in which phi increases to put the limits pi over 2. If you do other way around, it's going to kill this minus sign that you had from the direction. So this sb go away. I have a mu naught I over 2 pi times pi over 2, and there's a minus sign here. Okay, so be careful that although you've gone from here to here, when you integrate in phi, you're still going, phi range is phi is from 0 to 2 pi in that direction. It's increasing in that direction. This will be pi over 2 in that direction. So this integral d phi is actually the range of phi from the lower range to the higher range. Well, if you don't want to do that way, then you'll have to actually not include this minus sign here. You need to have a dl that way, and then you can use the opposite direction in which it went. You can have the information in the phi, or you can have the information in dl, but you can't have the information in both places because they are going to cancel each other out. Okay, so that's a circulation for this. I just want to say that this is a very common result, right? This is same magnetic field, but this was the same, but this got 0. And why is the case? And that has to do with what happened what will happen in Ampere's law. And let's just talk a little bit about Ampere's law beyond this calculation, okay? So what this magnetic field is, this magnetic field is actually of an infinite wire. And it carrying some steady current I. And so if you look at magnetic field at any point is kind of circulating around, is going around in this circles. And you use right-hand rule to get the orientation. Use right-hand rule to get the orientation of the magnetic field. So this is going around in circle around this current carrying wire. So if I go in any of these loops, say if I go here, I'm going to go in the same direction as B, then B dot dl will be whatever current that passes through the area of the loop. So the current I passes through the area of the loop. So B dot dl going through one of this oriented loop is mu naught I enclosed. So this one encloses this current. This one looks like a more weird loop, but so this one is like I go from here to here and then go over here and then I go all the way here and here. So I do this area encloses the current. The current is still going through here, through the area enclosed by this more complicated loop. But this loop, let's draw it out. Current is here. So I go from, in terms of loop, I go from here to here and then go like that, So this loop, this area, this current is not going through that area. This current is not going through. So the I enclosed is equal to 0. So that's why I got a 0 here. So this law goes by the name of Ampere's law. So if I knew what the current were, this particular problem did not tell me where the current was, just gave me magnetic field. And so I had to do all those integrals. But if I know where the current is, then circulation is very easy to get. Okay, this Ampere's law directly gives you circulation. In the future, we'll say by assuming certain properties of the circulation, I may be able to solve for B, magnitude of B. So here is a use of Ampere's law that you can see is coming. Is if I have a B dot dl and I have some is equal to mu naught I enclosed. So if somehow I know something about B and I know what the C would be, somehow I know this, okay? And I make an argument. So there's some argument I can make. Okay, so this is something that you have to learn to make the argument, that somehow this thing becomes B times some kind of L. This integral turns into that, and then it's mu naught some I enclosed. Then magnitude of B just equal to mu naught I enclosed over L. If, that's big if. It's not always possible, but sometimes you can do it. So the cases that allow you to do it, they're usually really very easy to solve for magnetic field using this. Okay, so what kind of cases for this kind of behavior? So one is infinite wire, steady current in infinite wire. Another one is you can have a solenoid, infinitely steady current in infinitely long solenoid. Maybe steady current in a toroid. This is an interesting structure. Steady current on a surface of a plate, infinitely long flat plate. Okay, a steady current on the surface, planar surface of an infinitely large plate. So these are some of the cases. Maybe I should add here. I should add here is 1B is steady current in an infinitely long cylinder. Now, when you have a infinite wire, there is no inside the wire. For a cylinder, you can have a magnetic field at a point inside the wire, magnetic field at a point outside the wire, and so on and so forth. So we are going to try to do these problems in the future. Actually, very next things. But I want you to memorize this formula. This is Ampere's law formula, and how to what the circulation means. How do you calculate circulation of a given magnetic field? Now, if you give a current structure, you can get the circulation like that just by itself. Let me also address that. Okay, I think let's finish up with the problems like this. Find the circulation around this thing. The current is given like that. Well, if I look at here, the current is going from, with the right hand rule, and the current is going in the positive direction. This is the positive orientation for this loop. So over here for C1 B dot dl, I don't need to know the magnetic field, just use Ampere's law, mu naught I. So that's for C1. If you look at C2, the current is going this way, but if I look at the direction, if I use the right hand rule, the direction of this loop is, this is the direction, this is the positive direction of the loop. The oriented loop has a positive and negative direction set. So if I go around the loop, this will be positive direction. The other direction will be negative. So if I do C2 B dot dl will be minus mu naught I. How about C3? Well, there is no current passing through this. So C3 will be 0. I really don't need to do any calculation there. 0, just from Ampere's law. C4 is a really interesting one, right? Let's look at current comes in and current goes out. Now with C4, that's the positive direction. So this one is current is going in the negative direction. So from here, this I enclosed will be minus I. And when I go in the same direction, the positive direction, this over here, the I enclosed will be plus I. So if I do the C4 B dot dl, I'll get a mu naught with minus I plus I, that's going to be 0. So this will be also 0. So sometimes this is tested to know if you know a couple of things. Orientation of the loops, was always going to, which side is going to be positive, is going to be negative, you know. So like to test this thing, why this is negative, you should know that orientation of the loop. These loops have orientation to them, and sometimes I like to put arrow here just to remind myself that this loop is actually oriented. It will become very important when we do Faraday law, because the orientation will be related on both sides of the equation, and you will need to be able to keep track of plus and minus sign in Faraday law. Here also, but most of the problems actually go in one way, and so in a particular problem it doesn't make a difference. Over here I just cooked up a problem where the loops were like C1 and C2 with the opposite orientation, and so it makes a difference here. But most of the problems to do with Ampere's law, you probably have just single orientation in the problem, and even if you don't know, it makes no difference. But sometimes I know there are people who like to test this. Do you know the orientation of the loop? So orientation of loop. This, you got to study that. Okay, take care. Bye.